Hi, welcome back to the Natural Language Processing Learn from Scratch lecture series. In today's lecture, we'll be looking into the Word2Vec model. Specifically, we'll be building and training our own Word2Vec model. Fine. So before getting into that, we'll have a quick recap of what we have done till now. So we started off with the symbolic discrete representation and then distribution representation of the text with implementation of one-hot encoding, bag of words, term frequency, inverse document frequency, and then bag of n-grams and all of those metrics, all of these different techniques for representing the text. And then we went for distributed representation, and we saw how word embeddings work, how are they useful, and then we saw pre-trained word embedding models like the Word2Vec and Glove and many other fast text and many other. But then we implemented these two alone. Fine. Okay. With those two things done, now we'll move on to our main content of this video. So we'll be training our own embedding. Fine. So before getting into the this particular whole mathematic notations, I know actually usually we have to start with mathematic notations, but then before getting to that, let me just show you the overview of different types or different ways we can actually train a Word2Vec model. So specifically, Google has used two specific techniques for training their own Word2Vec model. One is the CBOW or the continuous bag of words representation based model. And then we have the continuous skipgram model. So what do they do if you see? So how do they work? They get in some context of words. So within the whole sentence, they get in some context window of words, set of words for, and then for predicting a particular word in the sentence, they take up this context window, which actually says number of words after it and before it as the group of words that will be used for representing this word. And that is why it's called distributed representation. The reason why we call distributed is because the responsibility for representing this word is given to other words that are in the same sentence. Fine. So in continuous back of words representation, these other words are used to represent this particular word. And that is how you get this whole structure. So this is a normal small form of the same structure, and this is the node wise like or a deep learning based representation of the same structure. So here what happens, we give the words which are before it. As per the context window, we give the, if the context window is 2, then the two words before the actual word that is being aimed to predict would be given in, and the other two words which are after the aim word or target word would be given in. Fine. So these two words, left and right side of the main target word would be given in. Their representation would be given in, and the representations would be summed up to get an aggregated representation. And this would be used for your output layer. Here is exactly what is happening. So we get the input layer. This would be having a vector form. I'll tell you what is this vector form. Just observe this notation here. It's called x1k, x2k, xck. Fine. And then this is all aggregated to one particular dimensioned, one hidden layer. Through that, you'll get the actual summed up aggregated representation. And this is used for getting your output layer. Observe this W notation. W is one notation, and then we have W dash. Well, and see how the dimensions of this. V cross N. What is V here? The vocabulary. Why are we even using the vocabulary size? Because we would be getting the one hot representation for each and every word. Okay, fine. Now we'll get to the mathematical notation. So now you would have a glimpse of what it is. We'll now go to the mathematical notation. You'll have a better idea. Fine. So what did we see there? Okay. So we saw a vocabulary size of modulus of V. So what is this? What is this V here? V is the vector that represents your words. Fine. So V is the vector that represents your words, and then we have we told that this x1 is actually a one hot representation, right? One hot vector, meaning how do you represent the words in one hot encoding? We saw it in the first lecture, right? In the first part of this chapter of text representation. So how do we do that? We have a vocabulary corpus with us. We have a say vocabulary corpus of say like some many words. Fine. There'll be some group of words. There'll be 10,000 words or 100,000 words. Some those many number of words we have, and then we give it as 1 or 0 with respect to whether the word is there wherever this word is there in the vocabulary. That place alone will give it as 1. Remaining places will give it as 0, and we'll get the whole representation. So this is a one-not representation, one-not encoding representation. So it is very much 1 or 0 kind of representation, right? So this is what we use. This is the initial representation of the words for the Word2Vec model or any word embedding model. Fine. So we give this to make computers understand just the mapping between a particular symbol, which is a word, and how where is it positioned and how can it be represented. So this is your XW. Fine. And then we have the embedding matrix. Fine, you might ask me, where does the matrix even come here? Why are we even going for this? See, basically all the neural networks are composed of matrix. Each layer in a neural network, input layer and the hidden second layer, will always be connected via some connections, right? All of the connections are just weights. And since they are weights, if you actually, each node of a first layer will be connected to each node in the second layer, meaning it will have those many number of weights. Fine. So we have those many number of numbers representing or numbers connecting one node of a layer with the other nodes of the layer. So imagine this: for each and every node in the input layer will have the same number of numbers, like same number of connections. So each connection will have a number or a weight given to it, weighting number given to it. So all of these weights will be your coefficients for your input. For those people who don't know anything about neural networks, please first learn about neural networks and only then come to this particular lecture. If you know neural networks, well and good, just revise the concept alone. So all of these numbers that represent the connections are, for our mathematical computation, we represent them in a word matrix form and a weight matrix form, and that is your embedding matrix here. And what is the dimension of this matrix initially? It is modulus of V cross dimension. What is this D dimension? So I told you that Word2Vec model comes with different parameters, right? We can get a embedding for 100 dimensions or 300 dimensions or 500 dimensions. This is standard dimensions. How so? Though we have 1 lakh or 100,000 vocabulary corpus that represents one particular word, or if the whole vocabulary corpus or number of words in the whole document corpus that you have or data set that you have is 100,000, all of those words would be ordered, and they'll be, if you want to numerically represent them, you just have a one not encoding. We'll give 0 for representing a particular word in the sentence. We'll give all the other words at 0, and then wherever this word is there in the vocabulary in the order, that position alone will give 1. Remaining everything will be 0. That will be your one not representation, right? So how many rows are there in the vector? It will be 100,000, right? But then 100,000 very much inefficient for computation. That is why we map this to a smaller 100 dimensional or 500 dimensional or 300 dimensional vector, and that is exactly done using this embedding matrix. To save your time, I've actually written down all of the things here. So now you can see. So the word is actually now represented in the one not encoded form, first word. Now we'll have to map this vector with the actual embedding. So what do? We transform this vector or this matrix form, this row matrix. How do we do that? We transform it. How do we transform it? By multiplying it with another matrix. That would be your embedding matrix. So this matrix is just the weights of the neural network. Fine. So this would be of the dimension V cross 100. 100 is the dimension that we need. That is why it is like this. So you can directly multiply, right? So what would be the resulting matrix after the multiplication? How do we usually multiply? We do this way, right? Here for each and every row in the first matrix, we multiply it with the column of the second matrix. That is how we multiply. After multiplying it, we'll get, what will we get? We'll see. So we'll get the 100 dimensional actual embedding of the word, of the first word, just the first word. Fine. But then even this is not optimized. Just we are getting the representation of the first word. And then what do? We get some of, I told you, right? There are different models. So for one word, we'll represent it using the two words after it and two words before it. So we'll add all of these, we'll first convert all of these different words in the one hot encoder or one hot vector form, and then transform them using this embedding matrix, get into the preliminary embedded word embedding of 100 dimensions, and then add those dimensions for each word. Two words after the target word and then two words before the target word. We add all of that. And then what do we get? We get the OG embedding. That is the aggregated embedding or the aggregated embedding. I call it as OG because it is a sum of all of the four context window words is embedding together. So all of the 100 matrix, 100 dimensional row matrix would be added. And then again, okay, so now you got this matrix. So how do you actually train the model and then say whether this embedding really represents the word or not? How do you check it? So you have to use some form of decoder or something, right? Only then we can map the words with the the embedding with the one not encoder and then check whether this embedding is representing that word or not. So we had to have a decoder. So if you see closely observe this is actually almost like an encoder for mapping the embedding. This matrix acts as an encoder for mapping the embedding, and then we get the whole aggregated sum. Again, we decode it to cross verify whether this embedding is representing the words or not. So how do we do that? We use the output matrix. That is your output layer. Fine, this is what it is. D cross V, that will be your 100 cross. Here we need 100 dimensions, otherwise it will be 100 cross V. This is what you get. With this, if you multiply this again, what do you get? You get the 1 cross V. This would be a one hot encoder again. So the input and output would be a one hot encoded vector numerical form for a particular word. And then we use a softmax at the last layer to get this into this form, and then with that we'll be able to check whether this particular dimension is representing this word correctly or not. So that is how you cross verify whether this embedding is working or not with your output layer. This output layer will not just have the weight, it will have even the softmax. So it'll give the probability for each and every column in this matrix. The columns here represent the vectors, right? So the vocab positions, right? So it will be either 0, 0, 1 or something. So it'll say the representation directly, one not representation, one not encoding representation of the words in the vocabulary corpus directly. And then with this, we can actually cross check. There is even a loss function for this. We'll see all of that in the data part. But this is how, in an overview, this is how actually the whole mathematical process works. It's just a manipulation of this vector to make it represent this embedding, actual embedding that we want, and then decode the same embedding so that we cross verify whether this embedding is representing the word or not. So this is just a mathematical notation. Fine. Okay. Now we'll look into this. This is actually overall, if you see, it looks very much simple. Yes, it is simple, but then there are a lot of steps that go into it. Fine. So now we'll see the whole step-by-step process. Fine. So now we have the raw text corpus. So here we have this example sentence: the quick brown fox jumps over the lazy dog. Fine. So we get in this raw text corpus. What do we do first? We tokenize them. We split the sentence and then we tokenize them into small tokens of words. That is called pre-processing here. And then we define the context window. So this context window could be your number of words for the target word. What could be the number of words that you want to represent after it and then before it? That could be a context window. So here I'm giving it as 2. Fine. So we'll see how this works now. So creating the training pair. So as per the context window, we have to create the training pair now. So how do you do this? For this particular, we get in. So how will the training pair look like? we have in the input, it will be just the context words, all of the one not encoded context words which are there for this particular word brown. So you saw this particular sentence, right? Where is this sentence? Yes. So for this particular word brown, we have the quick and fox jumps. So here is what you have the context words here. So all of these context words are one not encoded, and we convert them into the one not encoded form, and then we give it as an input. So this could be a first data point. The first data point's input would be this, and the output would be the target word, that is brown. That will be one not encoded again. And for each and every target word T that is in one not encoded form, this would be your input and this would be your output. Okay. So now we'll look into how this data set or data pad will look like visually for each and every word. Fine. So for each and every target word here, the quick brown fox, see how the context window is moving slowly towards the right, and then how the context window is changing. The number of context words is changing, and the words itself is changing for each and every word, like for each and every target word. Fine. So you can see quick brown jumps over could be your context words for the target word fox. So this is how your input and output pair will look like, or the training samples will look like for the Word2Vec model training. Fine. So now we'll move on to the next step, that is your embedding layer. So here what happens, you first convert all of these words into their one not encoded vector forms. So one not vector forms. So we convert them into that form, and then we multiply those words, each of the words with their weight matrix W, to convert them again into the low dimensional dense embeddings. Fine. And then, like I told you before, like we had a transformation function. We add, a transformation matrix for transforming this particular uh, one hot encoded vector. We use a transformation matrix that could be your weight matrix, or it could be your parameters of your neural network. Fine. And we multiply them, and then we get the R needed dimensional row vector. That could be your embedded embedded layers output. So each of the context words will have this embedding layer to it, and then each of the words will give us an embedded 100 dimensional or a d-dimensional vector form from their actual one not encoding vector form. So it will be mapped to it. So after that, we have got all of these different words vector form, that is embedded 100 dimensional or d-dimensional vector form. So now what do? We aggregate those. In the previous example of the mathematical equation, I just said it is a sum, but it's not that simple. It's not that simple in reality. What really happens is we get the average of those. So I'll show you how this average actually takes place. So we have this hidden vector called h. The reason why we call it as hidden vector is because it's in between the input layer and the output layer. It is actually in the hidden layer. That is why it's called as hidden vector h. And how do we calculate this? We take the average. How do we get that average? First of all, we take the sum of each and every element in the matrix. Sorry, in the matrix for each and every word. For each and every word, we got this representation, right? This low dimensional dense representation, right? So all of these vectors would be added, and then they would be divided by 2 into m. So what is this m? We saw m as the dimensional, right? Sorry, the context window, right? So number of words after the target word and number of words before the target word. So usually for this kind of continuous back upwards representation, there will be 2 into context window. Context window, if it is 2, which means on both the sides, we'll take 2 words from the target word. So that is why it's 2 into m in this formula. We just divided by that. So we were essentially taking the average of their sum. Sorry, average of their 100 dimensional dense vector, and then that could become your final h or hidden vector representation for the word. Fine. So this would be the actual aggregated context vector. or the context embedding for the word. So now what do? You get this context embedding, you've aggregated, and then you've got this hidden vector edge. Now we move it to the output layer. Only while training we do this because we want to verify whether this particular context vector is representing the word correctly or not. And that is why we move it to the output layer. We feed in this hidden vector h into the output layer, and it is multiplied by another output matrix, that is w dash, and then it is the output of this multiplied product would be given into the softmax probability distribution, and that softmax probability distribution will give us a dimensional v dimensional meaning v or d. Actually, not D. V dimension. V meaning vocabulary size. Actual vocabulary size, the one not encoded representation had actual vocabulary size 1 cross V, right? Mod of V. That was the size, that was the dimension of the actual one not encoded vector, initial vector that we gave in as an input for this model. The same one would be given as output after passing through the softmax probability distribution. So it'll give us a probability, a continuous probability, but then the one with the highest probability will be given as 1 and the others will be as 0. And then with that, we get the output of this output layer. So you will see the equation here. So we first get the product, that is U, and then for each and every, for the aggregated word itself directly, we get this softmax probability. Fine. Okay. So after getting this, we use this probability, the softmax probability based output, as an input for getting the loss function, like for calculating the loss. How do you calculate the loss here? We use cross entropy. So we directly given the probability function into a log minus of log, and then you get this. So this is how you get this cross entropy loss. And then from this cross entropy loss, you can actually use it. You'll use this value for calculating your back propagation based gradient descents. So how do you do that? Again, it's very much neural networks concept. I'll just show you the equations alone. So we have the loss. We compute the loss by doing this, and then we update the weights for both the first embedding matrix, that is your initial weight matrix, and then even your output layers matrix, meaning both the hidden input layers, first embedding layers matrix, and the output layers, final output layers matrix, both of these would be updated. Matrix meaning the weights, both of the layers weights would be updated in this way. So this is the whole process, and here this n or this neta is actually called as the learning rate. This is a Greek syllabus representation of this learning rate. And W, how do you get the gradient descent? We do this with respect to the weights itself. Fine. So it will be, we'll come up with the optimal weight at which the loss is the least. That is the whole concept behind this whole weight updation and then gradient descent and then the back propagation technique. Fine. So we'll even implement all of this whole custom pipeline in our Google Colab. Okay. So, but then before going to that, let us see the overall structure of this whole pipeline. So how does it look like? Fine. So this is exactly how it looks like. So we have the words, the different words here, and see this annotation here, -1 and -2. Here the context window is 2. That is why the words which are before it, before the target word, 2 words before the target word and 2 words after the target word are given in. And here the vocabulary size is, you can count it here, 1, 2, 3, 4, 5, 6, 7, 8. So we are coming up with the what is the architecture of with an assumption that we have an vocabulary of just 8 words. So we have come up with a language that has only 8 words of vocabulary, and for that, in that case, this could be this could be your simplest Word2Vec architecture. So we represent these words in the one hot encoded, 8 1 cross 8 dimensional format. It will not be like this, like it will be like a row vector. Like don't assume that this, since it is in vertical format, it will be a column vector, but then in reality it is actually a row vector instead of a column vector. So it will be 1 cross 8 in this case. And it will be given in, we have the embedding layer. So each word would be converted into its 100 dimensional. So here we are converting it into 100 dimensional embedded layer. Each of the words will be converted into that way. And then all of that is actually taken in. And then we use average aggregation function. That is, you're adding each and every embedding layers value and then getting the average of it by dividing it by 4. In this case, it's 4 because it's 2 into m. M here is 2. M meaning the context window. Context window, what is the context window here? We are taking just two words after the target word, right? And two words before the target word. So if the context window is 2, it means 2 into m in the formula. 1 by h is equal to 1 by 2m into summation of sigma of the weight matrix, where actual matrix is for each and every word. So that is what you're getting here. And then after aggregating, we'll get a 100 dimensional vector, and that would be passed through the output layer with softmax. That would be giving us the same 8 node. Here the vector size is 8, and that is why we get this 8 node based uh, representation of the vector, and then this could be your one hot representation. In here is where we get the result, and then we compare it with the actual value, and then compute the loss function, and then update the weights. Fine. So we update the weights both for the output layer as well as the embedding layer. Fine. So this is the whole Word2Vec architecture. So now with this knowledge, you'd be able to build your own Word2Vec. Fine. So theoretical aspect of how Word2Vec works is properly done now. So here, this particular configuration is with dimensionality of embedding dimensionality of 100, context window is 5, and then the vocab size is 8. And that is why we have this. Fine. I hope you understood the whole architecture of Word2Vec. I think you can even build your own Word2Vec as well. But so we'll implement this overall Word2Vec architecture, our custom own training and building of this Word2Vec in Google Colab. You can even try it out yourself along with me. I'll be attaching the notebook in the video descriptions. Fine. Before going to the implementation, some of you might have this doubt on, I said the context window is 2, but then m is equal to 2, but then how is it given here 5? So here, this specific parameter what I've given here is actually the total context window. Like when going through the whole context window would be going through certain number of words in the sentence. Okay. So the with respect to the formula where the context window was m, that actually showed how many words after the target word and how many words before the target word we are taking in. But then if you see the number of words the system or the software has to go through in a sentence, that would be the total context window. That the total context window would be 5. You yourself calculate. You have the target word here, 2 words after it, and then 2 words before it. So 1, 2, 3, 4, 5. So 5 is the total context length, right? That is why I've given here as the context window to be total context window to be 5. In the formula where m is the context window, context size, that would be 2 words after the target and 2 words before the target. That is why it is 2 here. Fine. So I hope you understand that. Okay, fine. Now we'll go to the implementation. So now we'll see building our own custom word embedding model from scratch. So initially we'll be using this particular dataset called Wikipedia. So Wikipedia's text is available in this particular package. So we'll be downloading it. So I installed it. I've already run the whole thing. So I'll be just going through the code alone. Fine. So we just install this datasets package and then import the dataset, load dataset function from there. Can use this wiki text and wiki text to raw version 1, and we use these, we split them for training, and then we'll get the number of lines also printed here. So what you can see is 36,718 lines are there. Sampling is not printed properly here. Yes, it's not printed properly here. Okay. So we'll see what happens after this. So now what we're doing is we're just doing all of the basic pre-processing techniques that we learned before. So when doing that, we got to know that the original length or the number of characters is this much. How much is this? 1 crore, 9 lakhs, 29,707. Those many characters were there. And then after cleaning it, so many of them were actually even repeated also. So we removed all of the duplicates and then removed the punctuations. We mainly remove the punctuations and the multiple spaces. If we do that, we get this. So these are just the like just 100 characters, first 100 characters. It's all printed here. And then we have the first 20 tokens printed here. Even this is not perfectly done, right? So we need only the unique words alone. So we get the unique words alone from here, counter of tokens. So we use this and then we get the unique total number of unique words before filtering. There is even this filtering needed because sometimes this unknown token can also be used. So and then we are giving a minimum frequency of 5. Sometimes many words could be repeated, like the and those kind of words also could be repeated a lot of times, right? So we have given a minimum frequency threshold to be 5, so that if a particular word is occurring more than 5 times, then it will be included as a unique word. So after doing that, we get around 19,963 new or unique words in our vocabulary. So our vocabulary size is 19,963. So if you just print the frequency, you can just see the frequency of each and every word here. Frequency meaning the number of times a particular word has occurred. See, the most occurred word here is the fine. So okay, fine. Now we have the vocabulary. We are uh, we are having the proper vocabulary now, and it is all indexed with the unique numbers, IDs. Okay. Now we have the index also done, and we have set the context window to 2. So like how we have seen it for the architecture, our context window would be 2, meaning the total context window length would be 5. Okay. Now we are creating a class with the data set. So uh, this particular CBOW, that is continuous bag of words model, we'll be developing the model also, but then it requires a certain structure of data set, and that's why we're preparing the data set this way. So what is the structure of data set? We'll be picking out words in a sentence, like 2 words after the target and 2 words before the target, right? That is the pattern that it needs. So we'll be doing that exactly. So you can see it here, self context. So we get the context window and then multiply it by 2 and then we do this. So we can, the proper description of each and everything is given here. So if we properly go through each and every variable, you'll be able to understand this to its very minute nature. Fine. Due to time constraints, they won't be able to go through each and every variable. What is it even doing for each and everything here? Because it's a class thing, and I hope you know the OOPS concept for going through this. And these are all the functions. First of all, we are initiating the constructor and then coming up with the function called get item, and then the class definition is done. There is no particular attribute inside our class definition. And then we initialize this initiate this class with the token and the context window as context window, that is 2. And the batch size is 512. So it is adjusted as per our memory capabilities. And then the data loader. Data loader is the function that we had before. So we using that, we just create the data loader now with the data set and the batch size and all of that. Fine. So with this, you will get the whole context shape. So 5 and 12 number of sentences were taken out of, for each of those we'll have 4 words. And then all of those sentences will have 512 target words. And then the indices of the context indices and all of them are printed here. Fine. These are actually very much basic things. The most important thing is the model here now. So we are having this embedding layer that is already available in PyTorch. So we are getting this neural network and then directly getting the embedding layer. We are giving it again the vocab size, meaning this would be the input layer. and then the output of this layer would be the dimensions. So it will be connecting with this input layer, and then the output layer will be equal to this embedding dimension. And then we connect this embedding dimension to the linear neural network. That would be the output layer. So there will be two layers. In between these is where we'll be having our aggregation layer. Fine. So we have this, and then we forward it, and then we get the average. So here is where we get the average embedding. Fine. So you can directly see it here. So result, this is the whole model. So inside this, we have this forward, and then it's very much straightforward, man. Okay, so we initialize the model, and we got the model's whole architecture printed here, and then we train the model using the parameters, hyperparameters. So since we'll have to use GPU for this, because the data set is huge, and the model will be using these many parameters, like these many elements having vectors as the initial input itself. So it is huge. So it will be much better if you use GPU, and that is why to optimize our Google Colab notebook for GPU, I use this CUDA based optimization technique. So with this, you'll be able to optimize, and then we even added the optimizer for the neural network so that it can learn properly, and then learning rate is given, and then it uses cross entropy loss, like how I told before, like how we saw before. Fine. And then we do the back propagation and optimization technique. After doing all this, it will be repeatedly doing this until we get a good. Actually, I could have given an early stop. I didn't give it here, but then it is a simple custom word embedding model that I've built from scratch. So the loss is, as of now, it is not that great because I've not run it for more than like 1 or 2 hours. So, but if you can actually run this for more than like say 6, 4 hours, 6, 8 hours, with proper GPU, you'll be able to get your own word embeddings. And this is one of the reasons why we don't build our own word embeddings, because it requires a lot of compute power, and along with it, the data. The more data you have, and the more compute you have, the better model you can actually have. So that's why we don't usually come up with use our own word embeddings, but then it will be good experiment or a good learning exposure to you, so that you can learn how really the word embedding works. Maybe you could come up with a better architecture than this in the future. So it'll be a good exposure for you through this path. Fine. So, and then uh, now we have got the models word embedding detached, weighted on detached, and then got the embeddings alone. So if we get the shape of this embedding matrix, this would be the shape. See, it's become this. We told you, right? V cross D. That is the embedding matrix's dimension. This is exactly W. This is the W, and it's perfectly going with that. And then you can see how it's giving out the vector form for the embeddings of this particular word computer, right? Yes. So we can even create our own cosine similarity function here using our own embeddings. So with these embeddings itself, we can directly get this whole thing. So what are we doing is we're detaching. Why are we detaching this? The reason why we're detaching the remaining parts is we want only the embedding vector alone, because that is the main part, or that is the main like output or the utility of this Word2Vec model. The reason why we attached output layer along with softmax, and then we added a cross entropy loss, was to just make sure that to verify whether the embedding layer is properly mapping to the word or not, words hot one not encoded representation or not. So to train it in that way, we actually did that. But after training, could detach that last layer alone, and then get the embedding thing part alone, and that could become your Word2Vec word embeddings. I hope you understood the proper learned embedding matrix and how it works, and how are we using this to our advantage and all of that. Fine. And with the same embeddings, you'll be able to get the vectors, and then with vectors, we can directly apply the cosine similarity formula, and then get the cosine similarity score. And this is our own custom uh, function that we have come up with for cosine similarity. It's very much straightforward. No need to depend on your like pre-written packages or modules. You can write your functions also on your own. Fine, that is why it's from scratch. So with these different pairs, you can see how similar they are, how far away they are. We have not really come with the model is not really the best even now. But then even now, you can see how similar king and queen is and king and apple is. King and queen is almost more similar than even the king and apple. It means that almost the vector space, even when the training is not properly done, when it's not properly to the max, to its optimum level, even in that case, this representation is very much good in identifying the difference between a non-similar word or a contextually different meaning word. That is an advantage. That is the significant uniqueness of this Word2Vec model and this continuous bag of words based Word2Vec model. Fine. So with that, we conclude this implementation of Word2Vec. I'll be attaching this notebook in the description. You can actually experiment a lot. You can add even more layers. You can build your own different similarity score also if you want. And yeah, so enjoy learning. We'll see the next concept. So we are wrapping up this video. Till now, we have seen how to build and even train our own Word2Vec model from scratch in Google Colab Notebook. We even implemented it there. So, and then we understood the architecture step by step and even the equations that are there for each and every layer. And totally we have seen how it works, right? Okay. So before getting briefing on you on what will be seen in the next video, let me just show you this. Again, as usual, starting is easy. The next other portion should be completing this whole thing will be a little challenging. Only the 5% have achieved it. So the question is, are you going to be those 5%? You need to answer that. But then I have to be honest here, right? So connotations are making it to the module 9. So there's a module 9th video. So I've made it to here. You're very much close to 5%. You're almost here. So make sure that you are this. Fine. So you're very much close to 5%, but then you have to make it to this. That should be your aim. You answer that. You decide out of that. I can only say this. I can only tell you to be disciplined and be consistent. Make sure that you put on efforts to be disciplined and consistent. That is what I can tell you. You have to decide it. Okay, in the next video, we'll be learning about doc2vec model and then even the hand-crafted text representation techniques. Fine. So it's very much important. The handcrafted techniques are very much important. You might think that okay, handcrafted technique is like very much conventional. People are not even using that in a transformer age, right? But then that is not true. Like even now, many of the prominent industries are actually using handcrafted text representations. You won't believe it. You will believe it only if you see it in my next lecture. Fine. So we'll meet you in the next lecture. Until then, have a nice day then. Bye.